first of all, tomorrow will probably be the last day. We'll do underwater welding. We should finish electron beam lasers today. And it turns out to be somewhere Thursday. And I just kind of looked at things. It's probably, you guys need to get your rest, right? So I just announced tomorrow is probably our last day. Yeah. But however, you need to finish up if you're going to take the 3371. Yeah. Your back shows up on a number of the videos, I noticed. It's okay. In any case, yeah, you got to watch those other videos to learn about. And if you have questions about them, you can always come see me. Okay, so we're talking about lasers and electron beams, and both high heat intensity proceeds, but the physics of the materials interactions are very different. And we pointed out that electron beam, you heat by electrons, and therefore you end up with something on the order of 1 electron volt worth of energy of that electron coming in, and heating by photons with lasers, and you're talking about something that's 10,000 or 100,000 times less per particle, and therefore laser is all surface heating. There are enough free electrons when you hit a metal that it only goes a fraction of an atom deep. You heat beneath the surface with electron beam, and I'm not sure I told you the story, and all the heat here is on the surface. I'm not sure I told you the story of a problem that I believe it was Ford, but one of the automotive companies, might have been GM, this is a number of years ago, they were going to heat the cam followers on your camshaft. Okay, basically the kind of little lobe shape on the camshaft that makes the valves go up and down. And they originally had a laser heating process, and what the problem with laser heating, it's all on the surface, and so the maximum thermal expansion is right on the surface, and you get, when you cool down, the maximum residual stress is all right on the surface, and unfortunately it's tensile. In fact, the one way to think about residual stresses, I think this is in the other lectures that you watch on the video, is whatever stress pattern you have when the thing is hot, you have the opposite of that stress pattern when everything cools down. Okay, and I think I explained that in the other part of the thing. But basically, so if you heat it up and you have compressive residual stresses on the surface because it's hot and it expands, puts the surface in compression, when you cool it back down, that surface will have yielded, and when it cools back down, it will go into tension. So that tensile residual stresses, they got fatigue cracks when they did laser surface heating of these things. They went back to the manufacturer of the equipment, which I believe was Siaki, and they said, oh, well, if you have that problem, you should use electron beam, because electron beam, you actually have your maximum heating just beneath the surface, which means the surface is cooler than the layer just beneath the surface. That means that the surface layer, when you first heat it up, is in tension, because the maximum heat's just beneath the surface by maybe only 5 or 10 thousandths of an inch. But in fact, it puts the surface in compression after you've done your heat treatment. So this wasn't a melting process. They're just heat treating the surfaces of these things. But it turns out that by switching the process, they went from tensile residual stresses on the surface to compressive, and all of a sudden the things now met their engine required number of hours before failure. Okay, we said the sample must be electrically conductive. It turns out you can actually do ceramics by electron beam, and a guy, Roy Rice at the Naval Research Laboratory, did this about 20 years ago. He electron beam welded ceramics. It depends on the type of ceramic. A lot of times you end up with a nice crack falling right behind, but you can melt ceramics if you preheat it to about like 1,000 degrees centigrade, because ceramics, if you heat them to high enough temperatures, will actually start to conduct. And so if you don't need very much electrical conductivity, but you have to have some. And lasers will heat electrical insulators. In fact, they heat electrical insulators better than they heat conductors, because electrical conductor has free electrons, and free electrons tend to reflect the laser light. So the laser light is absorbed by the free electrons and re-radiate in all directions. So lasers like to heat insulators better than they do metals, whereas electron beams have to be essentially some metallic conduction. Electron beam requires vacuum. I think I talked about that some the last time. You have to have a vacuum to generate the electron beam. Now, people do go outside the electron beam with aerodynamic windows. There's a little company in Connecticut, kind of a spin-off of some stuff at Brookhaven National Lab, that's developed a new, better, all-purpose aerodynamic window for electron beams. And so they claim to have much better out-of-vacuum electron beam performance than we had in the past. I don't know exactly how far they're going to go, but that's what I've learned in the last year. It turns out laser is best in helium. And the reason it's best in helium is, I think I talked last time about the nail head type of a nice electron beam weld will usually look something like this. A laser weld, more commonly, will not have as deep a penetration, and it actually is the result of kind of two penetrations. And what happens is up above here, you have a vapor that's, both of these generate a vapor because you have such a high heat intensity. But if you have a vapor of metal up here, the laser is going to see those free electrons, be absorbed by those free electrons, and re-radiate from those free electrons. So it's like having a point heat source right above the surface, okay, rather than a sharp beam. You still have a sharp beam that drills a hole, so you get this finger down here, what they call the finger, but you also get this bigger, broader thing because essentially the laser has a hard time getting through that metal vapor. And in fact, the best thing you can do is blow helium transverse to the surface, because helium has the highest ionization potential and will generate the fewest free electrons when the laser hits it, okay? So it's best in helium. We don't use helium unless we have to because it's expensive. It turns out electron beam, if you, rather than doing it straight down, if you do it in the horizontal position, make your weld this way, you can get in deeper because the metal that melts tends to slough down to the bottom and the thing drills straight through. The problem here is when it sloughs down to the bottom, it fills up the bottom and you keep on having to push the liquid metal out of the way. So the process is more efficient at hole drilling if you're doing it horizontally because it doesn't have to get the metal by gravity slumps down and you get a deeper penetration, by about 30% in the horizontal. It turns out laser, if you had exactly the same heat intensity, you know, 1,000,000 watts per square centimeter, and it's the same spot size so that you have, let's say, a 10 kilowatt beam, laser and electron beam. It turns out the laser in the atmosphere will give you less penetration than in a vacuum. And the reason is this reactive force of the vapor coming out of here basically is fighting against the atmosphere. If you've got an atmosphere up here, if it's vacuum, it's just going straight out and you get better momentum transfer to dig the hole. It turns out if you happen to put the laser in a vacuum, there's no reason why you can't weld a laser in a vacuum. It's just vacuums cost money, so you don't usually do it. One of the advantages of a laser, you don't need a vacuum, okay? But if you put a laser in a vacuum, you'll get about 50% deeper penetration. And if you put it horizontal, you get about 30% deeper penetration because the physics of this sloughing is the same for lasers and electron beams. But in general, for the same powers, lasers will be shallower welds because you get this defocusing at the top, okay? And so you lose part of your energy. If everything else was equal, an electron beam will give you about double the penetration for the same power level. So those are differences. I'm going to get to cost, okay? We got about 14 of these things, okay? But there is a difference in cost, although it's, well, anyway. Number 6, the electrons penetrate the metal vapor in the cavity. I have a metal vapor that forms in here. That's what's helping drill this hole. And in fact, the electrons having, you know, on the order of 1 electron volt of energy can bounce around and still have enough momentum to reach the bottom of the hole, even if they hit some of that vapor. The lasers, on the other hand, 1 photon hits 1 electron, and it loves that electron, and it gets absorbed and re-radiated in all directions. Okay, so it turns out the plasma tends to decouple the beam and form the nail head that we've talked about. It turns out that electron beams are nearly 100% heat efficient. People have actually measured 99% heat efficiency. And when we're talking about that, we're talking about melting it. Essentially, you melt this whole thing, and while the melting's occurring, it's so rapid, on the order of 10 milliseconds or 20 milliseconds to drill this hole, you essentially have no heat transfer loss into the heat effective zone during that time, part of the process. Okay, so you get nearly 100% heat efficiency in terms of the area that you melt during the melting cycle. On the cooling cycle, all that superheated metal, the heat flows out, and then the heat effective zone grows around it. So the heat effective zone ends up being proportional in width to the width of the fusion zone. If I'm talking a 2-inch thick weld, I might have a centimeter wide weld, which means I could have a centimeter wide heat effective zone, which means it's actually bigger than an arc weld. Typical heat effective zone in a steel arc weld is not a centimeter, it's on the order of a couple of millimeters. So in very heavy section steel welding with electron beam, if I end up having a, let's say it's a 10-to-1 depth to width ratio, and I don't want to go too narrow because I miss the joint or it gets cockeyed and I don't completely hit the seam. 10-to-1 means the plate would be 2.5 inches thick if it's 1 centimeter wide. 1 centimeter wide, I'd end up with about a 1 centimeter wide heat effective zone. That's going to have big grain growth and poor fracture toughness, and we may talk about that in a little bit. So if you're talking very heavy plates, you end up with actually bigger heat effective zones in laser welding. And it's hard to read this, but it's nearly 100% heat, and the laser is nearly 100% heat efficient on a ceramic, but on on a metal, you have a lot of reflectivity. So you have the free electrons in the metal. The free electrons absorb the laser light and then re-radiate it. It turns out if I'm welding titanium and I don't do deep penetration welding, I would find that I get about 30% of the heat actually absorbed and 70% radiated. If I'm doing silver, copper, or gold, have very good electrical conductivity, lots of free electrons, I may only get 5% absorption. So in general, silver, copper, and gold and aluminum are terrible for laser welding. It's a serious problem. People would like to weld them. In fact, what do we make mirrors out of? We make mirrors out of laser mirrors out of copper. But then we gold plate them. And the reason we gold plate them is because the absorption is nearly 100% on a ceramic. You know what happens to copper if it sits around in the atmosphere? It tarnishes. Well, that tarnish is copper oxide. It's not as electrically conductive as the metal, and so if I got a little spot of tarnish on there, all of a sudden the laser light's going to couple into the mirror and melt the mirror, even if it's water-cooled copper. So basically you take copper and you gold plate it, because the gold doesn't tarnish, and you don't have problems of all of a sudden the surface absorptivity of your mirror changing dramatically as it oxidizes. The problem then is your high power reflective laser light, if you get some dust on that mirror, the dust is typically not conductive and it will absorb all the laser light. So I may end up with a laser beam that, before I focused it down, might be 2 or 3 inches in diameter if I got a 15 kilowatt beam, let's say, in a big laser. And I got a mirror and it's got some dust particles on it. I'm going to basically pit that surface and get a little surface melting wherever the dust hits the surface of the mirror. So it can be a pain in the neck. You know, it's all laser, moving the laser around is all done with mirrors, right? Well, the problem is you have to keep the dust off, you have to keep the surface from oxidizing, or your mirrors don't work. And if you're trying to weld the mirror material, you have a hard time because most of your power is being radiated away from it. It turns out, though, and actually I didn't bring it, I have a little sample of some tubes that were laser welded, aluminum laser welded. And aluminum laser welding is a lot better than it used to be. It turns out you run into some instabilities in the process, but the story I like to tell is kind of the exception that proves the rule. Let's say that the laser light absorption with aluminum is only 10%, okay? 90% is radiated away if I'm just melting on the surface. So if I have a situation where I have a weld pool like this, that's fairly shallow, I'll have 10% absorption if the base material is aluminum. On the other hand, if I put in enough power that I start drilling a hole like this, and the light gets down in here, it may be 10% absorption on this surface, but where does the light get reflected to? It gets reflected back inside here. And so the actual absorptivity inside the cavity starts approaching 100%. So we did some experiments once years ago on laser welding of aluminum, and we showed that if you're just welding on a solid aluminum plate, which researchers like to do, why make a real joint? Why just melt something that's already joined together, and then when you're all done, you joined it together, right? Start out as a single plate. Well, it turns out you'll get this type of phenomena, but if you actually have a real plate that has a slight gap in it, and you get your laser light in here, you actually can melt something fairly deep because you got a cavity, okay? And you get higher absorptivity. So it turns out in real aluminum welding with a laser, you need to put in like 10 to the 7th to get 10 to the 6th, because 90% of it's going off just by reflected heat, right? Well, the problem is if you get 10 to the 6th and you start to get this finger penetration, all of a sudden you're now absorbing 10 to the 7th. And what happens when you get 10 to the 7th? You got too much heat and you start blowing everything out. So it turns out laser welding of aluminum is inherently an unstable process. You got to put in 10 to the 7th in order to get the deep penetration. But once you get the deep penetration, your absorptivity increases, and now you're putting in too much power. And so you blow all the metal out, you lose your melting, you keep traveling along, and then you start the process over again. It turns out a number of years ago, just the exception that proves the rule, because aluminum is so difficult to laser weld, it turns out the world's largest application of laser welding at the time happened to be on aluminum. And the reason was, you've seen these little strips in double pane windows? And they take a piece of aluminum in cross section. It looks like this, okay? They're going to make a little channel, okay? And they're going to put the panes of glass on either side of this channel, right? And this is the separator. And you'll look, and not in this building, they didn't know about double pane glass back in those days, okay? But you go to a modern building, you look in there, and you'll see on that little piece of aluminum, you'll see on some of the older buildings, you'll see where it was laser welded. This thin aluminum was laser welded. Nowadays, they do some mechanical staking. A lot of times you'll find they just actually mechanically join these things together. But it turns out back 20 or 25 years ago, the largest application of lasers in the world was someplace, I think in Illinois, and they had like 20 lasers lined up, which back then, these were $1 million pieces of equipment. And they were turning out something like 300 million feet of this stuff a year. And the reason was they would run a continuous beam, but they would get these intermittent welds because the process is inherently stable. And it would just look like a perfect series of spot welds. But in fact, in order to get that, they had a continuous beam, and this beam was just continuously coupling and uncoupling, okay? So because the process was unstable, in that case, they got exactly what they wanted. You don't want a hermetic seal in this channel because the atmosphere changes, the barometric pressure changes, and you don't want pressure buildup inside the two panes of glass and stuff. So you actually want a little breathing in this, and so they would use laser welding because it produced an inherently imperfect weld. And they didn't particularly need strength, okay? So you can have whatever rule you want, and then someone will find an application that all of a sudden whatever you thought was a weakness becomes a strength, okay? Electron beam, the beam is distorted by magnetic fields, okay? In fact, that can be an advantage because with rastering fields, you can basically take that electron beam and you can make patterns on the surface. So if I want to, instead of welding, I want to do heat treatment, it's hard to generate an electron beam that's not a fine focus spot. It's actually relatively easy. I mean, you can do it, but usually the electron beam welding equipment is a very sharply focused, well-designed coils that give you a very sharp beam. But if I want to do heat treatment, I don't want a sharp beam with high heat intensity. I may only want 10,000 or 100,000 watts per square centimeter if I'm just doing surface heating. Well, it turns out all you have to do is put a simple coil on there and run a sine wave pattern at 2 different frequencies in the x and y direction. So you put a coil in the y direction, a coil in the x direction, you put 2 different sine wave frequencies, and what do you get if you put 2 different sine waves into an oscilloscope? Anybody know? No electrical engineers in here? You get a Lissajous pattern, okay? And I'm probably going to misspell this. Lissajous. And basically, if I have a sine wave of one frequency up here and a sine wave of a higher frequency down here, but 2 different frequencies, I will get a pattern in here, and you get these, they're actually very nice symmetric patterns, okay? But they just keep wandering back and forth because you're driving it at 2 different frequencies. If you drive it at the same frequency, exactly the same frequency, you would basically probably get a 45-degree slope right here or something. But if you drive it in a slightly out of phase, and the difference in phase is always shifting, okay, continuously shifting, you get this complex pattern, which will time average and not give you the problem if you had just tried to do a square wave oscillating back and forth and scan it like a TV scanner or a raster scan on a TV, right? If you try to do that, you always have a problem of acceleration and deceleration as you stop and start at each side. The advantage of a Lissajous pattern is when you come up to the sides, you're actually skimming it tangentially. And so you don't have these accelerations. It's always going at a constant speed. And you basically get uniform heating over the whole surface. Okay? So it's easy to distort it with magnetic fields when you want to. One problem that people have, the Japanese spent a couple $100 million in the 80s trying to weld 8-inch thick pressure vessels with electron beam. And it turns out, well, let's just talk about 4 inches and above. Turns out at 4 inches and above, you run into a problem in steels with electron beam, or you can. It turns out that first of all, you got a very high power beam, and you may have 100 kilowatts of power, which is not too hard to do. You can run a half an amp at 200 kilovolts and get 100 kilowatts of power in your electron beam, and you can melt and weld an 8-inch thick piece of steel in a single pass. And the reason the Japanese were interested in this after the second oil shock in 1978, what they called the oil shock, you know, big run up in prices. We're having one now, but we don't call it a shock. Huh? That's right, and that's not good for the elections, right? And actually, it's not as bad. There's not a bunch of big lines. People have now adapted, so it's not like the old days when they cut off the supply. You had a shortage. Okay. Today, the prices go up and the markets adjust, and it turns out there are plenty of companies. What happened within the, I have this theory that it takes about 10 years for industry to adapt to a major change. And the first oil shock was in '73. By 1983, companies had installed new capacity in many cases and, on furnaces and boilers and things like that, and they basically could just flip a switch now, and they can switch from oil to natural gas. Some of them can switch to coal. So it doesn't matter. I mean, before they were locked into oil, and they couldn't use any. Their only energy source they could use was oil. And if the price went up, they just had to pay a higher price. Well, nowadays, if the price of oil goes up and gas is cheaper on a BTU basis per BTU, you just flick a switch and you start using. These guys have wired their plants, basically piped their plants, I guess, to be able to use either one. In some cases, people use coal. And so nowadays, oil can try to increase, but it can't spike like it did in '73 because everything else will start to replace it. And people start using more coal. And so what did we see a year ago? We saw the price of gas go up, okay? And now gas is back down and oil's going up. And no one's been talking about coal, but I'm sure coal producers are just seeing their market increasing slowly, right? Because eventually you have competition for your energy source, okay? Anyway, the Japanese decided in the late '70s that they needed to build coal gasification plants, coal liquefaction plants, and these were going to be 30-inch or 30-foot diameter vessels. with 8-inch thick walls. If you started to calculate the pressures you needed to do the Fischer-Tropsch or whatever type of process. And so you can't move a 30-foot diameter, 8-inch thick vessel down the highways, okay? You can move components down, okay? It's sort of like a submarine, right? Maybe not quite as long, but it's a little heavier than a submarine, okay? Actually, it's a lot heavier. I'm not supposed to tell you how thick a submarine hull is. I know, okay? In any case, they wanted to weld these things in the field, and they thought, well, electron beam would be a good way to do it because you could do it all in one pass. Welding an 8-inch thick piece of steel is not the easiest thing in the world, okay? So basically, they spent several $100 million researching high-power electron beams to do this. One of the things they found is that if one of the two pieces of steel was slightly magnetized, remember about arc flow, and the current doesn't like high magnetic fields. So if I have a high magnetic field over here on your left, the beam will actually distort to the right, and I will get a the thing will actually come like this, and I'll miss my joint at the bottom. Well, that's okay. You can demagnetize your steel, although it's 8 inches thick and weighs, 50 tons or 100 tons. It's not the easiest thing to manipulate, but you can do that. But the bigger problem was when they wanted to weld dissimilar materials, when you get above about 4 inches, you cannot keep this beam from distorting, because you actually, when you have dissimilar metals, this is steel A and this is a different composition steel B, it turns out you will set up electric currents through here because of the temperature difference in two dissimilar materials. You got a chemical potential difference because of the different composition of the two steels. You'll actually set up currents. Those currents will generate magnetic fields, and you'll get the beam actually bend inside the material. No one's ever solved that problem, okay? Because it's an internally generated magnetic field. If you have an external field, you can eliminate it. Another problem is if there is an external field, the beam could bend before it ever gets here. Well, they got a simple solution to that. You just shoot it through a pipe, okay? If you're generating the beam up here and your workpiece is 2 feet away, you just put a 2-inch diameter steel pipe around it and shoot it through that pipe, even if you're in a vacuum. And that pipe, the steel pipe, will shield the magnetic fields, the unbalanced magnetic fields, enough that the beam will go through there straight. So anyway, beam distorted by magnetic fields, an electron beam. A laser, unaffected by any fields other than gravitational fields on a cosmic scale, okay? It will be. Einstein said that it will bend light, right? But we don't have to worry about that, okay? Electron beam produces X-rays. And in fact, because it produces X-rays, there's kind of two sizes of electron beam machines. Generally, you'll see machines below 40 kilovolts and 100 kilovolts or above. Why? Because getting down to the cost of the equipment, it really doesn't cost a whole lot more to make a 100 kilovolt transformer than a 40 kilovolt transformer. It's just a question of how many windings you put in each one of your transformer coils. And that doesn't change the price substantially. However, if you're below 40 kilovolts, the X-rays are soft enough that just your vacuum chamber, just glass, will stop 40 kilovolt X-rays pretty well. And you don't have to have any special shielding. If you are going to go to higher powers, and this next one basically says the current, and we'll talk about why, is limited to about 1/2 an amp. But if I want to go to more than 20 kilovolts in my electron beam, and for this heavy section stuff, they wanted to go to 100 kilowatts. If I want to go to more than 20 kilowatts and I'm limited to 1/2 an amp, I got to go above 40 kilovolts. So if I'm welding 1-inch thick material, I probably have to go to something heavier than, or higher voltage than 40 kilovolts. I like to stay below 40 kilovolts because then just the regular old vacuum chamber shields me from the X-rays. If I want higher power, I'm going to have to go, typically I'll go all the way up to 100 kilovolts or more. And there's kind of this never land in between 40 and 100 kilovolts. You don't see very many machines with that intermediate voltage. Why? Because at 60 kilovolts, you still have to have extra shielding around your vacuum chamber. If you got to pay for extra shielding, you might as well go the whole way and just put 1/4-inch lead all around your chamber, which is what you have to do when you have a 100 kilovolt machine. Okay, so it all has to do with the X-ray shielding. It turns out that lasers, aside the health hazard, is not X-rays, but invisible infrared. They're typically, most of them are in the infrared, and so you can't see it. It's not like this laser pointer. And you get reflections. And so typically, the laser welder still has to have, you don't have to have a vacuum chamber, but you have to have all kinds of mechanical interlocks to keep people from walking in there when the machine is on. So if you see a laser welder industrially, you're going to see, just like they have around robots, guards and gates and switches that keep people from being inside. I mean, they'll have movement sensors inside the operating area so they can tell. So if a rat comes walking through your work floor, you know, your machine shuts down, you know, to keep people from getting hurt, because you can't see the laser light. And the last thing you want to do is walk through one of these beams. Ruin your day, okay? Is also a problem because it's reflective. It hits the metal and it go bouncing around and do something else. In fact, I was playing here earlier. You guys aren't going to be able to see this very well. Maybe I can do it somewhere else. I was bouncing. Okay, you can see the laser light up there on the bouncing on the, okay? It's just reflecting off the surface of the table. But when I have something even more reflective, like my metal, then it bounces around even worse. In fact, I have, they got to be expired by now because they were in the mid-'80s. But I have a couple of patents on laser instruments because a medical, someone from a medical company came by once and they said, well, we have a problem. When people do laser surgery, you want to do very fine cutting of human tissue, you can actually cut through it with a laser. But one of the problems is if you got other metal instruments in there and you hit, if your doctor accidentally hits the metal instrument and the laser light that you're trying to cut with reflects and cuts some other part of the patient that you don't intend to cut, right? It's not what the doctor wants to hear. So they wanted to come up with some material that would carry the heat away. They actually wanted a laser backstop so that you could put it behind with the tissue you were cutting and absorb the heat and carry the heat away, but absorb the laser light, but also carry it away. Well, it turns out that's sort of a contradictory thing for a material, because in order to have good thermal conductivity, it means you usually want good electrical conductivity in a material. Good electrical conductivity means it reflects the laser. Well, I want to absorb the laser, but have good thermal conductivity, and they usually go together. In fact, there's something called the Wiedemann-Franz law that is a relationship between thermal and electrical conductivity. It says that they're correlated. So I said, well, too bad you can't use anodized aluminum. They said, well, why not? And I always thought medical instruments were made out of stainless steel. I said, oh, we use aluminum in the instruments all the time. I said, well, that's all you need is you just anodize a piece of aluminum, and now I have a ceramic on the surface which absorbs laser light very well because it has no free electrons. It doesn't reflect it. And you also have, just beneath that surface, you have a high thermal conductivity material, aluminum, which will dissipate the heat. So it turns out we were able to go to 100,000 watts per square centimeter on anodized aluminum with laser light and not get any surface melting, because we were absorbing all the heat on the surface and we were carrying it away through the aluminum for these spots. And we ended up with 2 patents, which must be expired by now. But anyway, it was a simple idea. It turns out all you needed was any sort of non-conductive surface on the order of 10 microns thick, which is 1/2 thousandth of an inch, and then a high conductivity material underneath. Okay, so it's invisible, it's in the IR, it's reflective. People have to wear special glasses that'll absorb the IR light, so because if the laser gets in your eye, this thing has a warning on it. It says, don't shine it in my eye, okay? Why? Because your eye focuses it all at one spot. So this may not be high power, but if it gets in my eye, it is high power. In fact, the green light's really neat. I could shoot it all the way across the courtyard and sit in my office but it has to be not dark. I mean, during the day, I can only get out to about the columns in the Great Court and see it. But this morning, you know, it's still dark. You shoot it through the light, shoot it through the window, and you go all the way across to mechanical engineering. Okay. Now, you have to be careful if you get a green laser pointer, right? You know why? Particularly if you're around policemen. Okay. You paint a policeman, right? You call it painting the target. Now, if you watch, what was it, Patriot games or whatever? Okay, just use the laser and paint it, and that's where the sniper's going to shoot, right? Or whatever, right? Anyway, policemen get very upset when they see a green laser light on their uniform. Anyway, okay. So we get to fraction spots. Okay, it's current's limited to half an amp. Why is the current limited to half an amp in an electron beam? Because when I have electrons coming through here at more than about a half an amp, they're close enoughly spaced together, they start repelling each other. I can't focus my beam when I get to more than half an amp. So laser welders rarely go above 1/10 of an amp or 2/10 of an amp, and almost never go above half an amp because you can't focus the beam any tighter than that because of mutual repulsion of the electrons. In a laser, you get to fraction spots, okay? A laser is multi-mode, and the best mode for welding is what we call the Gaussian mode. If you want to think of the Gaussian mode, you can have a wavelength in this direction, in the X direction, and in the Y direction you can have another wavelength, and the two of them will peak in the center. You'll get a Gaussian shape with the highest power here. However, if I have another mode where I have a full cycle across here, and a single half mode here, I'll get plus up here, plus down here, minus and minus, because I have additive effects here and subtractive effects here, and all of a sudden I got a checkerboard in terms of my laser power intensity. And this is something that was given to me by Hitachi a number of years ago, where they basically had a 5 kilowatt laser. One of the typical things they do is they hit a piece of polymethyl methacrylate. Okay, not Lexan, which is polycarbonate, but anyway, polymethyl lucite. Okay, typical piece of polymethyl methacrylate, just a cheap plastic. You hit it with the laser absorbs it. If you hit it with the pulsive laser, it will vaporize the plastic, and it will leave behind the pattern of the laser energy. In this case, this was a 5 kilowatt laser. This was the size of the beam that was being generated, and it was going to later be focused to a smaller spot. In fact, what they have up here, if you look through here, you'll see they hit it and had about a millimeter of vaporization of the plastic, and you'll feel, or you can see the real dimples on here, and that is the multi-mode wavelength of the laser, and you can see the additive and subtractive areas of heat intensity. In this other case, they took that circle and they rotated it in one direction with a mirror, and they got an ellipse. And the ellipse gives you a higher heat intensity, so if I was trying to do heat treating with this laser, I can get a higher heat intensity, and if you look on the top surface, it's just an ellipse. Okay. This is one I think I picked up at Ohio State or someplace. It's another laser piece of plastic that someone hit with a laser, and you can see this is one where they're trying to get the Gaussian beam, but it's not perfect down in here so far as that goes. And you can see some radial or circumferential lines. So they're probably doing something with the polarization of the light as well. So you do have to worry about the quality of your beam, okay? It's easy to manipulate the beam with magnets because it is affected by magnetic fields, and you can use that to your advantage. Over here, you use mirrors and fiber optics. Some of the really interesting things nowadays, Professor Yoel Fink here developed a perfect mirror. It is theoretically perfect because he basically puts on different layers of materials with different refractive index, and he can get reflections that are required quantum mechanically. That, you know, just like you can only have certain energy levels of electrons in an atom, it turns out there's certain things when you talk about reflection of light. If you have layers of different refractive index material, you can have certain wavelengths that are not permitted to pass quantum mechanically, okay? So he developed something called the perfect mirror, and he's now building some of these things into fiber optic cables so that you can now use put a high power laser down the cable. And this is going to allow people to essentially have 1 kilowatt lasers where they can transfer the beam not with mirrors, but they can just use a fiber optic cable to carry the power. In the past, they were limited to about 1 kilowatt. I've heard of people putting lasers together at some of the national labs of 20 kilowatts and doing fiber optic transfer. So now you can imagine having a robot with a fiber optic cable moving the laser beam around wherever you want it, and you don't have all these problems with mirrors and gold plating them and keeping the dust off and everything else. So you can use fiber optics. The last area here is actually not the last, since I was asked about cost. Sample heats uniformly, okay? They got enough power in these electrons, and they come in and they ended up heating the sample because they bounce around a few hundred times or a few thousand times, striking different atoms in here and thermalizing everything uniformly. The problem or advantage, as well, the Naval Research Laboratory found that if you use high power lasers to try to weld steel, steel's got non-metallic inclusions, little ceramic particles in there, and those heat more efficiently. And what they found is that when they laser welded the steel, they basically could blast out the inclusions and vaporize them preferentially to the metal. And so the laser welded metal on HY80 was cleaner than the original HY80 in terms of reduction in inclusions. And it actually gave some better properties in the weld than you would have with the normal thing. Now the question about cost. They both cost around 1 million watts per square centimeter, and they always will as long as I teach this course, because you know, it's dollars per capital cost of equipment. I don't want to change that little rule, right? It turns out to put together a high power laser welding system, a few years ago the Navy had a demonstration in the Mantech program to put a what they call it wasn't the PAWS program. PAWS was programmable arc welding system, which is about $10 million. This is kind of a robotic welding cell. And that was about $10 million for a shipyard. But they had another one that was done by Don White and some other people up at in Minnesota by, can't remember the name of the company. They make MTS, Materials Testing Services, which is a guy who from MIT started this company to make materials testing machines. And they had a contract for about $10 million to build a laser welding cell for thick plate so the Navy could put small parts in something about the size of this room, okay? Small parts for the Navy, right? And up to probably 1 inch thick. And that was a $10 million system. A typical, and that's because you got a great big gantry robot and everything for something the size of this room. You're going to be moving things that, you know, weigh tons in and out of the cell. You got to shield the whole thing. The laser itself for something like that may have been $1 million or a couple of $1 million for the high power laser. You used to be able to figure about, what was the number? Was it $10 a watt? So if you had no, it was more than that. Anyway, but lasers typically, the prices have been coming down, but typically the laser might cost 30% of your overall processing equipment cost. Remember I said that because these are such high heat intensity processes, you have to automate, and they go so fast, you have to automate the process. So in a typical laser system, you might spend 30% of your capital cost just for the laser, the other 70% for the robots and everything else, you know, the manipulation and the high speed and the safety to keep the beam, you know, people out of the beam and stuff. In electron beam, you might be able to get the beam a lot cheaper, probably only 10% of the cost, but you have to put it in a vacuum chamber, and that's more expensive. So it turns out they both cost about the same when you're talking about the whole system. If you're talking about generating just the beam and doing nothing with it, the laser is probably 3 times the cost. But you don't have the same kind of peripheral cost because you don't have the vacuum requirement. So right now, and it really depends on what you're talking about, but the systems are similar. Now it turns out the big application of lasers is not for welding. And I already mentioned that laser and electron beam tend to be used in either the aerospace, where you have high value added, you can afford this high capital cost equipment, and you may only have a duty cycle of 2% time. There's not much uptime, but you got really expensive equipment, so you can amortize the cost of this expensive equipment over some really high value added parts. Or the automotive business, where you need this high power density and you have enough material to put through there to keep the thing busy, and you can get 40% duty cycle or something like that because you have enough material to keep it busy. So it's either aerospace or automotive typically. And the electron beam market is not a huge market, okay, because they are so productive. They're so limited in the number of applications. The number of electron beam units sold in the world each year is like 100. I mean, it's not tens of thousands, okay? It's not a huge number. And in fact, if you want to buy used ones, hey, I had one I could have given you a couple years ago. General Electric gave it to me, okay? It's originally about a $2 million system, and I bought it I got it for the cost of shipping it out of their plant and moving it to another new location, which is about $25,000. And I finally just gave it away because it was costing me about $8,000 a year just for the electricity and the water to keep it running, just the utilities, okay? The student finished his thesis, and I didn't want to pay $8,000 just to let it sit there in mothballs, in a sense. So there are all kinds of operating costs on some of these types of things, but the general cost is on the order, let's say, of $1 million for something. The biggest application of lasers, and they are now starting to sell thousands of lasers, metalworking, but not for welding. I mean, it's still in the few hundreds. And lasers are nice because you don't have to have a vacuum, and the prices of the lasers are coming down. So if they used to be 3 times the electron beam, well, maybe they're getting down to 20% of the electron beam. And I've now seen some things where people are getting enough power out of solid state lasers, like this, where you have very high efficiencies compared to the gas lasers, which people used before. They're getting some, I actually was up at Toronto this past summer, University of Toronto, and actually University of Waterloo in Canada, outside of Toronto. And they had a little $400,000 laser that wasn't much bigger than this. Of course, the power supply was huge, but I mean, the laser itself would fit on a robot. You don't have to use fiber optics to carry it there. It was a solid state laser, and it wasn't much bigger than a baseball, and it was all solid state laser. But the big application for lasers is not welding, but cutting. You go anywhere now, you go to a little job shop here in eastern Massachusetts and want to get some sheet metal cut, it's likely they will have an NC laser cutter. And you just put the sheet in there, you punch into the computer what you want, and the thing just traces it out. The big application before metalworking was cutting textiles, okay? Most of your shirts and pants and everything else, they'd stack up like 10 stacks of cloth, and they just cut the whole thing out with a laser. Okay, all 10 at a time or whatever. They may be doing 20 or 30 for all I know right now. But they're actually selling thousands, if you include the textile industry, they sell thousands of lasers nowadays, okay, for cutting sheet metal and for textiles. So, okay, well, we'll see you tomorrow, and it'll be the last formal class tomorrow.